that if all the dimensions are below 100 nanometer, we can call it as an zero dimensional material. It can be a quantum dots, nanoparticle, or even a fullerene. Next. So, next slide please. One dimensional material, as sir has shown as a nano wire or nanotube. Nanotube can be considered as an one dimensional material because two of dimensions of it is in the nanoscale and only one dimension is larger than 100 nanometer. So such kind of material is called as an one dimensional material. Next. Two dimensional material is, of course, whose one dimensions is at nanoscale and two dimensions are larger than 100 nanometers. So two dimensionals are more than 100 nanometer and only one is in the nano range. So that is nothing but usually this thickness you can consider if it is in the nano, then it forms a nanofilms, nanosheets. Graphene, as sir has said, if you cut open the sheet, even a carbon tube, that kind of material can form a two-dimensional material or even a nano coatings for that matter. So what is three-dimensional material? Then 3D material are not nanomaterial as per se. If you club them as an arrays, and if that individual material falls outside 100 nanometer, but as a group and bulk they can fall into the nano. So that kind of thing is called as a 3 materials. These are actually cannot be considered as a nanomaterial. None of the dimensions are at a nanoscales. So these are considered as in 3D nano materials. So zero dimensional nanoparticles, fullerenes. One dimensional material can be a nanotubes, nanohorns. Two dimensional materials can be nanosheets and nano layers. Three dimensional materials can be nanowire arrays and nanotube arrays. So group of these wires, you can say kind of arrays. So that can fall into the 3D material, 3-dimensional nanomaterial. Next slide please. So why small is good? Actually, sir has already introduced the concept of SA area, that is surface to volume ratio, how it affects and how it changes the surface property completely, how this change in the, or how these exposed molecules can lead to more reactivity, more catalytic activity. So that is what the base concept. Nano objects are faster, they are lighter. Nano objects get into small spaces. As we all know, in human, we need to penetrate the cells, we need to pass various barriers. In that case, nano is quite easy as compared to other systems. Nano objects are cheaper, more energy efficient, and different properties exhibit at a smaller scale. So if you see a surface area, if we cut open this 2 mm by 2 mm kind of a cube, if you make it into a smaller section, which is fragmenting, that is a bottom down approach you can say. And what happens after that? Next slide. The same cube, if you see, a surface area can be calculated as a height into width, number of sides. Cube has 6 sides and how many number of cubes. If you see, surface area for this is around 24 millimeter, whereas surface area for this cube is around 48. Why this change happens? Because we have cut open this cube into a different smaller cubes, which forms 8 cubes in total. So 6 multiplied by 8, because 6 faces we have, it forms around 48 faces. So as more number of molecules are exposed of the same part, so more number of opportunities are there for that molecule to interact with the surroundings. And naturally, more reactivity will be there, more catalytic activity will be there. So this is how this volume ratio, because volume we have not changed, the same cube we have divided. So volume will remain the same. But whereas if you consider this ratio, surface area to volume ratio, 24 by 8, it comes around 3. But if you see here, after the cutting it, we have got surface area to volume ratio around 6. So naturally, this enhances the properties at various levels. Next. So surface area, of course, hidden surfaces got exposed. As surface area to volume ratio increases, greater amount of substance come in contact with surrounding. And naturally, the result in better catalysis, since greater proportion of the material is exposed for the potential reaction. So this is how catalytic activity gets increased. Next slide. Next slide, please. So nanomaterial properties, first thing, have relatively large surface area, more chemically more reactive, and of course their strength and electrical properties also get affected, usually get increased. Second, they goes into the quantum realms, you can say, and begin to dominate. These properties of quantum properties begin to get dominated at this scale. A bulk material should have constant physical property. If you consider and compare with the nanomaterial, bulk will have similar kind of physical properties, but at quantum level this is not the case. So there is great chance that there will be changes in the properties. Okay, so size dependent properties are developed, such as quantum confinement can lead to semiconductor particles, can lead to super paramagnetism in the magnetic materials. So these properties were not there initially when material is larger, but it can develop into the material. Okay, next slide. So as we can see here, gold, a best example, yellowish substance, metal that we all know, and it is inert at a largest, at a normal condition, at a bulk volume, it is inert. But if you break it down and if you convert into a nanoparticle, gold nanoparticle, it exhibits completely a different scenario. So gold AU nanoparticles appear red if it falls into the range of around 3 to 30 nanometer, which is red metallic transparent kind of thing. If you go further, gold clusters, that is orange nanometric, if it falls below 1 nanometer. Same materials showing different colors. This is possible because of just size and shape. These are the two things that determines what kind of light scattering they will result into, and how the same material behaves differently, which was once inert and that have converted into a much active material. So gold nanoparticles now being researched a lot. So AU nanoparticles is an excellent low temperature catalyst that can be utilized for the reaction. So nanoscale size effect, one more example here. Physical properties, melting point get changed, chemical properties like reactivity, electrical property, mechanical properties, optical properties all get changed. Same silver sphere, when it is having around 40 nanometer, it shows around violet color. But same silver when have 80 nanometer size, kind of a grayish, greenish color. When gold sphere falls in the range of 50 nanometer, shows greenish color, whereas if you consider a silver nano prism form is there, so it show at 100 nanometer it shows kind of orange color. So shape also affect the of course the scattering of light, and that will also lead to changes in the color. So such kind of material can be used as a diagnostic tool. Next slide please. So as sir has already told, nano is not a new thing. Many people have used it. So in our daily practical routine, soot we see through the flame can be of a nano range. So 1000 years ago, Chinese used gold nanoparticles for coloring or dyeing their ceramic porcelain, which was kind of a quite permanent color, which is not ready to fade. Even a Faraday have developed kind of a colloids, gold colloids, which was stable almost till a century, almost up to World War II, which was kind of a of course the same material showing different reflection of different colors. So this was in the history. Even bhasma that we use in our Indian tradition is also a kind of a nano material, you can say. Many of the inorganic material, and from ashes we make it, and there is a whole long procedure and much research is going on that also. So that is also a nano material. Okay, so this is also one of the example. Lycurgus cup. This is from the 4th century of Roman glass cage cup made up of dichroic glass. So dichroic glass is the glass which can show a different color based on the reflection of light. If अगर आप सामने से देखते हैं, so if you see red when light from behind, when light falls on from the behind, that cup appears red. Where when light falls from front, it appears kind of a green. So that is what the difference that we can see in this cup. So this is also a phenomenon which was in the 4th century Roman glass kind of a cup that was developed, and kind of an example that it is not a new thing. That dichroic effect is achieved by making the glass with tiny proportion of nanoparticles of gold and silver. They were merged, and that dispersion have led to this kind of a different coloration. Okay, so this concept is already there, which was not new. Okay, but in medicine, after the famous talk, people have started working towards its application in terms of medicine. So there are two approaches how you're going to make nanomaterial: top down and bottom up approach. Top down, where you are building something by starting with larger components. So you are kind of a sculpturing, okay, taking a big rock and removing the unnecessary part. So that is kind of thing, top down approach, where you get a nanomaterial by cutting down the unnecessary thing. Whereas bottom up approach, where building something by assembling a smaller component, like assembly. So atom by atom, like a crystallization, one atom on that kind of additive manufacturing, where small molecules join together to develop a nano clusters, nano assemblies. So this is kind of a bottom up approach. Now this is about the basics. I suppose I've covered quickly. Now we'll go into the functionalization. Again, and functionalization, I have picked up a few examples so that I have not dealt all the cargos in detail. I am just going to dealt with what cargo means, how they can be utilized, because there are n numbers of methods. If you want to develop liposome, you want to develop a nanotube, if you want to develop a dendrimer, there are many vesicular systems and all they have different methods of preparations. So if you see, drug delivery is a method of administering a drug to have a therapeutic effect, and to have a maximum therapeutic effect we don't want the side effects. So that is what off-target effect we don't want. Conventional therapy, of course, is exposing drug to unnecessary receptors, and untoward side effects are usually faced. So most common ways of drug delivery that we all know, and an ideal therapy should minimize the risk of causing adverse events, and at the same time they should elicit the intended therapeutic effect. Please go ahead. So these are two famous systems that we actually follow: matrix system and nanocapsule systems. We all know in matrix, drug is embedded along with shell, polymer shell, and in shell core system, nanocapsules, where drug is inside and polymer is covering and controlling the release, and at the same time protecting the drug inside it. Okay. So nanomedicine can include pharmaceuticals, nanodiagnostic, nanotherapeutic, and nanobiomaterials also. So all that can become a nanotechnology. So why there is a need then? So of course there are drawbacks for these conventional therapeutics. They have poor aqueous solubility, lack of selectivity, non-specificity, systemic toxicity, low therapeutic index, drug loading was a challenge, multi-drug resistance was there, efflux transporter were there in many of the cells that efflux the drug out, it is not able to penetrate the cell, need of repeated administration. So all these are the drawbacks that already all of us knows. So what are the advantages that nanotechnology offers? Please next slide. So it protects the drug inside and outside the body, enhance the drug permeability, better pharmacokinetics and distributions, and prevent interaction with non-target cells. That is very important, that if the surface property of cargo or that particle is such that it should not interact with non-target cell which we are not interested in. So thereby prevent off-target toxicity. Okay, next slide. So concept of magic bullet was coined by the Paul Ehrlich, who said that there is a possibility if we could do a selective targeting of drugs by putting a hypothesis of magic bullet in the year 1907, and Ehrlich formed an idea that it could possibly kill specific microbes which cause a disease in the body without harming healthy cells, without damaging our healthy cells or healthy organs. So that is what the concept which was pioneered, the targeting kind of thing, targeting concept. Next slide. So what do we mean by nanocargos then? Cargos simply mean a vehicle, okay, which is a carrier to carry your drug. So it can be anything. So a nanocargos or nanocarrier is a nanomaterial being used as a transport module. Okay. So which generally carries a drug. Along with it can carry a diagnostic material. It can carry n number of things. As sir has also told, a multifunctionality can be possible with this. A commonly used nanocargos includes nanoparticles, micelles, polymers, carbon-based material, liposome, very very famous because compatibility point of view, it has a phospho kind of a similar biomimicking nature that with your skin, that is with your cell, and that is why this lipid phospho combination plays very important role in avoiding toxicity. At the same time, you can say bypassing the endosome or reticuloendothelial system, RES system. That is the protective cells of our body which protects a foreign material by killing it. So our body need to avoid it. You must have heard the story of Trojan horse in a Troy movie. So in that Troy movie, they used to worship a horse, and they have very strong walls, and no enemy can invade. So in that case, what they have done, they have created a big horse where many of the troops, they have entered in it, and it was just kept close to the walls. Troy people have seen that, they have said it is a good signal from the deities, and they have allowed it to take inside their gates. And in night, many of the troops came out and Troy fought. Okay, so that was a story that we have to, you can say, a stealth way. We have to bypass or penetrate our drug into the cells. Okay, so that is what the function of nanocargos. Nanocargos can be utilized to obtain the goal of securing an optimal therapeutic effect, whilst at the same time minimize the unwanted side effect. So modifying the surface of carriers in a favorable fashion, that is what we want. So multifunction kind of thing is possible, as this diagram dictate. Aptamers are there, various drugs are there, small interfering RNAs are there, then tumoral markers are there, which are some kind of protein which are overexpressed at the tumor site. For example, HER2 receptor in case of breast cancer. So can we utilize this protein and put it on our cargos, so that specifically that delivery system will go and target to the tumors in the breast only, without affecting unnecessary exposure to the normal healthy cells. So that kind of concept was developed. So siRNA, peptides, PEGs, polyethylene glycol, we are going to see it is very important thing to avoid, even to have a normal surface, or you can say inert surface. Fluorescent dyes for diagnosis, carbohydrate, antibodies, dendrimers. So there are many ligands, small molecules you can attach, and you can functionalize the nanocargos. Next slide. So liposome, dendrimer, micelles, all these are the types of nanocargos. Vesicular system, there are plenty. Okay, I am not dealt with the process of making it, because it will be a kind of not a job of 1 hour. You need to have, you can see and study their making methods or manufacturing method. They are quite available. Next slide. So if you see here, what my talk is about, nanoparticles or nanomaterial, which can be of various type. It can be from metal nanoparticle, can be a combination of organic, can be a combination of inorganic and organic. It can be a plain inorganic material like mesoporous nano, MSN, mesoporous silica nanoparticle, or it can be a protein drug conjugate. It can be a solid lipid hybrid nanoparticle. So if you see, all of them must have this size range. They should fall in the range of 1 nanometer to 100 nanometer. Then we can call them as a nanomaterials. And of course, their shapes definitely affects their movement, their ADME, pharmacokinetic dynamics, and their effects also. So that is also we need to tune according to our need. And of course, this is how we are going to target them with the surface functionalization. So pegylation or surface functional group by attaching carboxylate moiety, amine moiety. Of course, most of the cells carries a negative charge on its surface. So if you charge with or coat with certain polymers having a positive charge like amine functionality, or for that matter, modifying a chitosan by making it into a trimethyl chitosan kind of thing, we are modifying the property. And if you coat this polymer on these nanocargos, targeting and specificity increases many fold as compared to normal cargo. So that we can possibly do by modifying the surface charges. Then targeting ligand, as I've said, antibody, peptide, and aptamer, these are famously being researched nowadays. So we can put antibodies specific to particular targets and receptor, and that will carry, that antibody will carry to that site only, that cargo will be carried to that site only. So that kind of a targeting capacity is possible. Next slide. So what are the benefits of doing or utilizing various cargos? It prolongs the longevity of carrier. As I've said, pegylation, famous thing. Stealth nanoparticles. Stealth means stealth means going undetected. Okay. So how you can do? By making it pegylated. So doing a polyethylene glycol coating on certain polymer, you make the surface more stealth, so that no body's immune system cannot identify it, so that it bypasses the reticuloendothelial systems, which have endosomes and many enzymes to kill, to degrade, to break that cargos. So you inactivate or you bypass that. So that is possible with pegylation. Then identify the cancerous cells by putting various kind of ligands. Efficient penetration, control drug release, diagnostic tooling is possible. Stimuli response can be possible. Targeting ability with specific ligand is also possible. Next slide. So surface functionalization can be termed variously. Okay, few people call them as a surface coating. Some of them will call it as a surface modified. These are the same terminologies. Surface decorated, surface anchored, surface engineered, surface conjugated. All these implies the same meaning, that you have modified the surface of nanocargos. Next slide, please. So surface functionalization of nanomedicine is done for this reason: to enhance the cellular internalization, to enhance the cellular penetration. आपका ड्रग सेल में जाना चाहिए. दूसरा, नॉन साइटोटॉक्सिसिटी, सेल में टॉक्सिसिटी नहीं होनी चाहिए आपके कार्गो की वजह से. Then improved payload binding capacity. Drug should be loaded on cargos in a more amount. Loading capacity should be increased. Then this is the actual objective behind functionalization, and that can be tuned for the specific recognition required for biosensing. अगर किसी रिसेप्टर को, या जैसे मैंने कहा HER2 receptor, where breast cancer proteins can be utilized to target the tumors, specific tumors. So that kind of sensing, biosensing is possible by surface functionality. Okay, and as I've discussed, stealth stealth properties that can be built into by coating the nanocargos. Next slide. So surface functionalization can be done by small molecules, can be done by surfactant, can be done by dendrimer, can be done by polymers like chitosan and many others. So there are two types again: non-covalent conjugation, आप सिर्फ surface पे coat करते हैं, या फिर synthetic conjugation, where you do certain reactions and attaching that moiety, ligand moiety, to by doing some reactions. Okay, so that is called as a covalent kind of conjugation. Next slide. So if you see here, there is a plethora of materials that you can attach to the cargos. So it can be a peptide, small molecule, antibody, aptamer, or it can, these are all targeting ligands. Then it can carry therapeutic agents along with drug. It can carry DNA, RNA material, hydrophilic shell for that matter, PEG, polyelectrolyte or polysaccharide can be coated on a polymer to make it functionalize. And imaging agents, of course, many of the time ferrous oxide nanoparticles, okay, usually are applied along with gold nanoparticles, can be attached, and of course they can be targeted. Of course they have a kind of a fluorescence, while as a separate entity they have fluorescence, but once they attach on the nanocargos, there is a quenching effect, that their fluorescence will decrease. And once they will attach on the cell surfaces, again they will regain their kind of a fluorescence property. So this difference will help us in identifying readout how much molecules of gold nanoparticle anchored with this diagnostic material have targeted or penetrated the cells. So can you go ahead? So these are the three major reasons why we do the functionality. We want to have a targeting, minimize the delivery to unintended site, lower the toxicity, imaging purpose, that is optical and electronic properties that allow cellular imaging. We can see the cell internalization, whether drug has been actually reaching to the site of action or not. And at the same time, we want a therapy to have improved therapeutic effectiveness, maximum therapy we want. Next slide, please. So this is the kind of a prototype example. Unmodified NPs, we have polymer strands, emulsifier, drug fluorescent marker we can probe in. This is the kind of molecules. Then we can attach to it surfactant as in surface coated NPs, and we can attach kind of a ligands, just a representative, so that ligand conjugated NPs can be prepared. Next slide, please. So functionalization using small molecule ligands. Which are the type of small ligands that can be utilized? One of the examples I have shown here, that nanoparticles with electrostatic force is complex with GFP. GFP is nothing but a green fluorescent protein. It is a protein that attaches to the nanoparticle, and that to differentiate the penetrability between cancerous cell and metastatic cells. How in a murine model, how the penetrability affects or how it targets the specific tumors. So please go to next slide. So if you see here, GFP in independent way, it has a fluorescence, but once it get attached to your nanosystems, fluorescence get off, or kind of a quenching, means decrease in the fluorescence is noted. That you can read out, and that you can see the difference, that yes, loading have happened, मेरे कार्बो पे fluorescent molecule attach हो गए हैं, and then once it enters into body and get attached to the cell surface, they regain their kind of a fluorescence. So fluorescence get on. So if you see here, various kind of ligand molecules, ligand head groups you can manipulate. आप play कर सकते हैं इसके साथ, और उसके वजह से आप targeting ability बढ़ा सकते हैं. So if you see here, NP3 have shown a better diagnostic ability or better penetrability in case of a metastatic cells. So this is a possible just by attaching or functionalizing the nanocargos. So surface charge, the next important property, as it is said that cationic polymers has a better penetrability or better targetability on the cell internalization. Usually cell carries a negative charge, but most of the time negative charge material also in some of the cases have found to have a good diffusion into the cell penetration. If you have an inert surface, that also is important to avoid the untoward side effects. So positively charged magnetic ion oxide nanoparticle, if get attached to dendritic guanidine, so this head group, it has shown that it has almost equivalent kind of a penetrability as that of your HIV tag peptide. So almost equivalent property if we could use a positively charged ferrous magnetic oxide nanoparticles. So positive particles are more effective as compared to the rest of the charge, negative or inert kind of charges. As compared to that, positive charges are better for penetrability. Next slide. Then comes the next challenge, intracellular delivery. It is very difficult, and this is the first hurdle in a therapeutic delivery, that how that molecule is going to get reached and released into the cytosol. कारण your cell structure also has a cytosol. There are various endosomes are there. जैसे ही आपका कोई foreign particle आ जाता है, endosomes cells are ready to engulf that and to degrade and metabolize that. So if you want to target a certain DNA to target a nucleic acid, it becomes very difficult, okay, to target that DNA. So you need to coat such kind of nanocargos with nuclear signaling peptides. So nuclear signaling peptides will make it or will not be that endosome will not be able to identify, and that have proven to target the DNA and affect the nucleic acid material and kill the tumor cells. So this was one of the technique that was used in case of intracellular targeting. Next, how this endosomal escapes can be endosomal escape can be there. For example, it has observed that unintentional functionalization with ligand is not helpful, but if you could create alterations of or striations of anionic groups along with hydrophobic group, alternative way, you have better penetrability. Instead of just putting a ligand for targeting, instead of that, if you could do the striations of alterations of sulfonate head group along with hydrophobic group, you have better penetrability. That has been observed. Okay, next. So payload on a surface. As we all know that most of the drugs are loaded on the surface, not internally. So in case of MSN, mesoporous silica nanoparticle, you can, and it has been, there are research papers out that you can have a genetic material as a grafting or as a functionalizing material, and you can load a drug inside the pore, because mesoporous silica nanoparticle has a lot of surface area where you can have a maximum loading. So please, next slide. So here this kind of a structure is there of this silica nanoparticle. So you can load a much amount of drug. So, and you can have plenty of options for targeting antibody, protein, folate for that matter, okay, transferrin and many other. By liganding it, you can target a specific purpose, whatever you want. Please, next slide. So polymer functionalization of nanoparticle. We have seen about small molecule. Now I am dealing with polymer functionalization, how to do it. But before that, we must know what do we mean by EPR effect. Usually passive targeting happens by this. That cancer अगर है तो cancer cells को nutrient की ज़्यादा ज़रूरत होती है. It has a leaky vasculature. More kind of a lymphatic drainage is there. Okay, and that is why most of the nutrient will be traveled, and the same phenomena is there, which can be utilized for passive targeting. Most of the nanoparticles will go there naturally and will get will attack, or rather, which is called as a passive targeting. The same EPR effect can be utilized, but how to keep your cargo system or how to retain your cargo system, or its retention time in the body, circulation time should be increased. So that is why still kind of a pegylation is possible. In that way you can increase the circulation time of these cargoes inside a body. So this is why pegylation is important. Okay. So one example given here is a pegylated gold nanoparticles were decorated with various amount of human transparent. Nowadays series of human transparent decorated gold nanoparticles are available for research. So it provides a better stabilization. If you put a pegylated nanoparticles even in a salt solution, we know that electrolyte destabilizes the colloidal composition. Okay, it aggregates it. So its property has been stabilized by doing a pegylation. Next slide. So these are all the advantages of doing a pegylation. It increases the biocompatibility, increases the increased size to avoid a renal clearance, increased solubility because of PEG chain, increase the blood circulation time. That is what we want. अगर आप pegylation से naturally passive targeting अच्छा हो रहा है, उस पर अगर functionalization कर दे तो और अच्छा targeting अच्छी होता है. So protection from reticuloendothelial system, active and passive targeting is possible of bioactive, and protection from proteolytic enzymes. All these are the benefits of doing a pegylation or coating with polyethylene glycol. Next slide. So this is one example where two combination of passive and active targeting was utilized. Here gold nanorods were prepared and they were utilized with EPR effect. They were targeted to a tumor site, and after reaching there, these gold nanoparticles were irradiated with infrared laser, and because of that, it have worked as an antenna, thermal antenna, where they have raised the temperature of the tumor site. And this tumor site, of course, have led to accumulation, protein accumulation. Then this kind of a stress P32 kind of a signals can be released from this, and that naturally attract further nanoparticles, which are kind of an iron oxide nanoparticles or nanowires, which is in a liposomal delivery. So that can actively targeting the same tumors where these gold nanorods have been accumulated. So this is a kind of a combination of passive and active targeting which was feasible by combining both the approaches. Next slide. So here we have the example of physical adsorption and chemical conjugation. Drug loaded nanoparticles by we have utilized, for example, a polymer which is a mucoadhesive. So mucoadhesive polymer, for example, a chitosan, we can have a positive surface on it just by a physical adsorption. But where in this case, ethylene diamine carbonamide we can utilize, and we can further treat the functional moiety, this carboxylate moiety, and try to convert into a kind of a amine functionality, hydroxysuccinamide treatment, and after that we can adsorb a chitosan on it. So you can convert and make it into a chitosan modified PLGA kind of a nanoparticle, which can be utilized for functionalization. So this is example of chemical conjugation. Next. So now there are plenty of tools or ligands are available. So lectins are there, odorolectin, wheat germ agglutinin. I'm not going into depth, just to make you understand this you can use in your research also. All these are the ligands that you can utilize for your nanocargos. So for transparent, iron rich, holotransparents are there, iron free apolactoferrins are there. In polymer case, chitosan, glycol chitosan, NNN trimethyl chitosan. In case of lipids, sterilamine is there. Cell penetrating peptides, for example, TATG analog, low molecular weight, protamine. All these are, there is a long list, of course. So we can, depending on the disease, depending on the cargos, you can select any of the ligand for having a active target. Next slide. So this is two case studies I have just taken to understand. So this is a NNN trimethyl chitosan modified flaxseed oil based mucoadhesive neuro-nano-emulsions. So the author have prepared neuro-nano-emulsions for direct nose to brain drug delivery. So purpose is to enhance the residence time. Mucoadhesive बना रहे हैं तो nasal में residence time naturally बढ़ेगा और drug controlledly brain तक पहुंचेगा. ये assumption है, objective है. And at the same time to enhance the mucosal permeability. अगर contact में ज़्यादा रहेगा तो permeation भी शायद बढ़े, ये objective है. And to develop a biocompatible, biodegradable, stable, non-invasive drug delivery system was the purpose. Okay, next slide. So design was applied, central CCD design, central composite design, where plus minus alpha level given by software, and oil and surfactant concentration, which was two major you can say parameters that were utilized as a variable, whereas my dependent variable was globule size and zeta potential. Zeta potential, of course, very important in case of a colloidal system. It tells us about the stability. So that was my intention. So here neuro-nano-emulsion 9 was assumed to be a kind of optimizing based on various observations, annotatable and all. But here we observe that globule size is around 32 and PDI is 0.2, whereas zeta potential was around 38. Plus minus 30 is considered to be a good zeta potential. Whereas in case of mucoadhesive nanoparticles, which is having a coating of chitosan here, so that's why we have got a positive charge here in a zeta potential around 80. Okay, and globule size was also around the same thing. Please go ahead. So it was after studying a bioadhesive study, we could find out that mucoadhesive neuro-nano-emulsion was found to have a 6.5 times greater bioadhesivity as compared to the normal neuro-nano-emulsion. Okay. And apparent permeability coefficient was also found to at a higher side, around 4 times more as compared to the plain neuro-nano emulsion. Please go ahead. So after taking a time, we could see that coating was observed around the emulsion particle. So we could guess that yes, proper coating was there. So it was observed that in both brain homogenization model and also in case of brain concentration versus time profile, that we could get a sustained release of this mucoadhesive neuro-nano-emulsion, and in all these cases, the brain homogenized model, rat brain was isolated, and in that we have taken a sampling how much drug has reached to that. It was found to be highest in case of mucoadhesive nanoparticles or neuro-nano-emulsion. Please next slide. So this is second case study where mannose anchored trimethyl chitosan nanoparticles were developed for pulmonary targeting of etiophyllene. Selective targeting करना चाह रहे थे. Next slide. So mannose ये sugar we have anchored on our chitosan, NNN trimethyl chitosan. We have anchored mannose. We have confirmed it with NMR. And after that, we have done two in vivo studies, in vitro studies by cascade impaction, pulmonary pharmacokinetic we have done. Through HPLC analysis, we could analyze that yes, drug has reached to the target site while by doing a mannose anchoring. Go to next slide. The same scheme is explained here. Please next slide. Confirmation of methylation and mannose anchoring on trimethyl chitosan. And this was a proposed mechanism that yes, thiourea structure was getting created by reaction between TMC and mannose group, isothiocyanate group of mannose, and that lead to a kind of a targeting functionality. So thank you all. I was kind of guessing. If anybody has any queries regarding this, can ask. I hope it was not quite boring. So thank you all.